This is Dr. S. P. Arsa from Mechanical and Industrial Department, IT Roorkee. I am going to deliver my lecture 24 on the course of the strength of materials, and this course is developed under the National Program on Technology Enhanced Learning. Prior to start this lecture, because in this lecture we are going to discuss about how to draw the shear force and bending moment diagram. We just want to discuss about the previous lecture to refresh your ideas. That in the previous lecture we discussed that if we have a beam, and if beam is under the various kind of loadings, then how we can relate the shear force as well as bending moment, because we found that if a beam is there, irrespective of what kind of loadings are there, irrespective of whatever the supports are there, then how these bending moment variation is there, or how the shear force is there, and that too also we discussed about that what exact correlations are there. So in the previous part of the previous lecture, we discussed about that if we have a beam and if it is loaded by a point loading, or if it is the cantilever or a simply supported beam is there, then how this force balance is there, and because of the force balance we simply cut the section in between, and we separated out these beam into two different sections, and these two sections we analyze that what the resultant force is there, and if the resultant force is acting irrespective of whether it's a downward or upward, then what is the relation is there in between these portion and the other portion. Then we found that there is the resultant of these applied forces, means when we applied the force from upper side and there is a reaction forces are there from the downward side, resultant of these things comes out with the shear force. So we decided that actually when the shear force is there, then how we can confine into a sign convention. So we found that if the shear force on the left portion of the beam is acted like that, means on the top side like this and bottom side like that, then we need to take the positive shear force, and on the right side if the shear forces are like that, if it is if it is going on top side and if it is on the bottom side, then it is of the negative shear force. So just keep this thing in your mind that actually on the left side, if your left portion is going upward and right portion is going downward, you need to take the positive shear force, and on the right hand side if your right portion is going upward and left portion is going downward, then you need to take the negative shear force. Similarly, we discussed about the sign convention of the bending moment, because the resultant of the applied forces also is going towards the bending moment, because whenever the shear force is there, the bending is also started to occur, and again a kind of virtual bending moment is there within that particular structure. So if we are saying that if this beam is under the balance condition or the equilibrium condition, then we need to analyze that how this variation is there and what is the resultant is there on that. So for that, what we need to do, we need to first of all find it out that what the sign convention is there which is correlating to the shear forces, because both are interacting to each other and both are simultaneously applied to the concerned beam. So actually if we have a the beam, and again if we cut the section by dot line, if you remember that part, then we found that if due to the these applied forces on the left portion, if the resultant of these forces, if the resultant of these forces going towards upward direction, that means if we have a tendency of beam due to these applied forces is going upward direction, that means in the clockwise direction, and if you go to the the other part of that, that means the right part, the resultant of those forces tending beam to go towards the upward direction, that means this direction is there, the bending, that is known as the sagging portion. If this is sagging is there, we are always taking the positive the bending moment, and if it is a hogging, that means if it is going downward from both left as well as the right hand portion, that means the counterclockwise and the clockwise direction, if it is like that, then it is known as the hogging the portion, or we always take the negative bending moment. So these are the two main sign conventions are there for considering shear forces as well as the bending moment. Then we discussed that actually if we have a simply supported beam, or if we have the cantilever, or if we have on that particular these both of the portion, if you have a point load or UDL, if UDL is there, that means uniformly distributed load is there, then since the uniformly distributed load is always acted just Newton per millimeter or kilonewton per millimeter, so what we need to do here, we just first of all we would like to see that what is the center of mass is. So first you locate that part and then multiply W into dx, whatever the dx length is there, then you see you have a concentrated load, then the total effect of the concentrated load will be coming into the moment part. So you see we discussed that actually what exactly the relations are there in between the shear force, bending moment and the applied load. Then we found that the shear force is nothing but equals to the partial derivative or exact derivative of dm divided by dx. That means you see whatever you see the shear force will come, or the resultant shear force will come wherever the change of bending moment is there with the domain. So since you see we are taking our the beam in the x location, or we can say the longitudinal axis, so our variation in the domain in the x direction only, so we can say that the shear force having a relation with the bending moment in that form, shear force F is equals to dm by dx. And simultaneously we can also correlate the shear force as with the this point of loading. So we found that the loading point W, which is you see kilonewton per millimeter is there, or we can say kilonewton per meter is there, we can also we can simply set up the relationship in between that W is equals to df by dx, or we can say that W is equals to the second derivative of d2m by dx square. The meaning is pretty simple, that now what we have, if we have a beam which is under loading of uniformly distributed load, the relation is pretty simple, that the load which is applied, it caused the shear force in a domain of the x in a first derivative form, that is df by dx, or we can say that it caused the bending moment in the second derivative, that is d2m by dx square, if we have the variation in the x axis. So you see this relation is very important. Now if I am saying that, you see with that relation, what we have now, two relations were there, which is very important, which we are going to discuss in our lecture, that first F is equals to dm by dx. So if I am saying that we have a point where there is no shear force, because you see we are saying that this beam is under balanced condition, that means you see if variation of this shear force is there, that there is a certain point where there is no shearing force, that means you see dm by dx is equals to 0. That means where you see the shear force is 0, we have a constant bending moment, because you see dm by dx is 0, that means moment is constant. So keep this thing in your mind, that if you want to calculate, you see any portion, that means you see in the beam, that where is the maximum bending moment, where is the minimum bending moment, where is the maximum shear force, where is the minimum shear force, we can easily correlate, you see, with the using of these relations. And that you see in this coming lecture we are going to discuss all these issues there. So first we would like to draw the bending moment and the shear force diagram, just to have a feeling that you see when a beam is there, irrespective whether it's a cantilever beam or simply supported beam, and you see either the point loads are there or universally this uniformly distributed load is there. Under these applications of load, what kind of the shear forces are coming, what is the nature of those things are there, what is the magnitude is there, and simultaneously what you see the bending moment variation is there, and what the magnitudes are there. So first of all we would like to have this kind of feeling. For that the foremost application is that we need to draw the shear force as well as the bending moment diagram, and through that you see we can easily know that actually how these variation is there, and we can find out the nature of the shear force as well as the bending moment diagram under the application of this force. So here in this lecture 24, you see we would like to discuss first how we can draw the shear force and bending moment diagram. So here is, you see, on your screen we find that we have a procedure for drawing shear force and bending moment diagram to have the feeling. So the advantage of why we need that, the advantage of plotting a variation of shear force F, which we are using F generally, and bending moment M in a beam as a function of S, because you see we found that this F is nothing but equals to dm by dx, or W is nothing but equals to df by dx or d2m by dx square. That means you see the variation of shear force as well as the variation of this bending moment is absolutely varying with respect to the x. So they are the function of s, because they are varying with they are not having the constant value with the x. So you see here, if I am saying that if I just want to plot the shear force F or bending moment M in a beam as a function of x, which is measured from one end of a beam, is that it becomes easier to determine maximum absolute value of shear force as well as the bending moment. Because you see if that's what I told you, that actually we just want to have a feeling that how this shear force variation is there and how this bending moment variation is there. So we can easily find out that actually okay, if these kind of loads are there, where is the maximum bending moment is there, where is the maximum shear forces are there. So you see only we can have a feeling if we know if we can draw the shear force as well as the bending moment diagram. Further, the determination of the value of m as a function of x becomes a paramount importance so as to determine the value of deflection of a beam subjected to a given loading, which is very, very important, because if somebody wants to design the beam, he should know that actually where is the maximum deflection, where is the minimum deflection, so that like we can simply put the factor of safety against that kind of loading, so that whatever the displacement or whatever the deflection is there, it can be minimized, or else we can go for the material property. So, a shear force diagram can be, now you see, come to the shear force diagram first. A shear force diagram can be constructed from the loading diagram of a beam. You see here, because how these loadings are there, based on the loadings we can easily find it out that what the algebraic sums are there of a applied force. That means, because we know that this whatever the forces are coming, they are coming in terms of the point load irrespective or the UDL. So, how the resultant of these magnitudes of these forces are there, we just want to find it out by using this algebraic sum. So, for that what we need to do, we just first the reaction must be determined always, because you see we have a simply supported beam or we have a cantilever in which this one rigid end is there. Whenever we apply the load, always there is a reaction is coming from the support end supports or wherever the supports are there, either the irrespective of the pin joints also. So, first of all, when we know the amount, whatever the amount which we are putting on the beam, first we would like to see if the beam is in the statical indeterminate form, then what the reaction forces are. So, first of all we would like to see that what reactions are there and how these reactions are varying. Then you see the vertical components of the forces and reactions are successfully summed from the left end of a beam to preserve the mathematical sign convention as adopted, because you see we know that since we are cutting the section of a beam in right as well in left as well as the right end, so we would like to see that how these shear force variation is there, and once we know the whether it is a positive sign or negative sign, then we can easily sum up those forces with the corresponding sign convention, and then we can draw these shear force diagram with the standard sign conventions. So, you see here, after getting the real feeling of the algebraic sum of the forces, we can easily put those shear forces on a beam. The shear at a section is simply equal to the sum of all vertical forces to the left of the section. That is what we discussed. When the successive summation process is used, the shear force diagram should end up with the previously calculated shear reaction at right end of the beam. That means, you see, once you started your force calculation from the left end, whatever you see, you can even start from the right end, but it is pretty easy for us to analyze a beam under the action of forces if you are starting from a left, so that you see since it is a function of the x, so we can easily find it out the resultant of these forces, like you see if it is started from extreme end, or if the middle force is there, or if it is pretty close to this the left end, or even the reactions, whatever the reactions which are coming towards the vertical directions, we can easily find it out that actually how these forces like these the algebraic sums are there. So, better to start from the left end and then find it out that what exactly this particular shear force variation is there towards the right hand direction. So, you see we can easily calculate the shearing reactions at the right end of the beam also, wherever the supports are there. No shear force act through the beam just beyond the last vertical force or the reactions. That is a very, very important thing, because when we have a support and whatever the force application is there, if you see this beam is there and at the end you see this reaction is there, and whatever the vertical forces are there, if they are collinear or coinciding, then there is no, you see the resultant is there, there is no shearing is there, if there is no eccentricity. And if it is going beyond the support reaction, or if there is no vertical forces are there at the particular end, then we cannot go to consider, then we cannot consider the shear force beyond this region. If the shear force diagram close in this fashion, then it gives the importance, just important task actually on a mathematical calculation, that if you go beyond those things, or we can say if the extension is there, then how this variation is there, because in that you will find the bending moment in comparison with the shear forces. So, the bending moment now is the real good importance of that. So, for drawing the bending moment diagram, it is always obtained by processing continuously along the length of beam, because m is a function of x from left hand end, and summing up all these areas of the shear force diagram, giving due the regard of to the sign. That means, you see we know that the relation between the shear force and the bending moment is what? is f equals to dm by dx, or we can say m is nothing but equals to integration of f into dx. So whatever the area which is covered by the shear force diagram will give you the bending moment, whatever the area is there, okay, because m is the integration of f into dx. So here you see from that, like the formula, we can easily calculate the moment if you know the area under like which this shear force diagram is coming. And only the problem is that actually what the sign conventions are there. So whatever the like the concerned sign conventions, we can put simply on the bending moment also. So the process of obtaining the moment diagram, from the shear force diagram by summing up is exactly the same as that for drawing shear force diagram from the load diagram, because we discussed that w is equals to df by dx. So f is nothing but equals to integration of w into dx. So you see whatever the load diagram is coming, if you simply draw the load diagram, and whatever the area which is under this load diagram will give you the shear force. So like these are all analogous is there, only the quantitative as well as the qualitative changes are there. Just like you see, if you want to find it out the shear force, then what you need to do, you need to draw the load diagram, just check it out, the area under that particular load diagram will give you the shear force. Similarly, you see, like if you want to find it out this bending moment, what you need to do, you need to simply draw the shear force, take the area under that particular curve and find out the bending moment. So these, but the important thing is that actually what the direction of these the forces are, or what the direction of these shear forces are there, and that corresponding, like the shear force diagram and the bending moment diagram can be easily drawn. So you see here, it may be also observed that at a constant shear force produce a uniform change in a bending moment, resulting in a straight line in a bending moment diagram. Because you see, if I am saying that the bending moment is constant, that means dm by dx is also constant. So obviously, you see, if I am saying that there is a constant change is there in the bending moment with respect to x, so there is a straight line is coming in the moment diagram if we have a constant shear force. If no shear forces exist, that means f is 0, a certain portion of a beam, that it indicates that like there is no change in the moment is there. Simply, like you will find that dm by dx is 0. That means, there is no shear force is there, so it has a least contribution to induce the bending, like inside the being portion. So it may also further observe that, like the dm by dx, which is f, as I told you, from the fundamental theorem of the calculus, we can easily get the value of maximum or minimum moment where the shear force is 0. Because you see, generally if you want to find, let us say if m is a function of x, and if you want to find out its maximum or minimum value, then what we are doing here, we are simply deriving the first derivative of that function, putting equals to 0, find the location of that where it is maximum or minimum, and then you see simply put those like the values in the main function and get the maximum or minimum value of the whatever the function is. So here you see, we are dealing with this kind of relation with the bending moment, dm by dx is 0. So we can get the location where the maximum or minimum bending moment is there, and once you put those values in the main function, you can get the real values that actually where at what location you can get the maximum or minimum bending moment and what is the value of bending moment is concerned. So in order to check the validity of a bending moment diagram, the main thing is that the terminal conditions for a moment must be satisfied, because you see, if it is not satisfied, then there is an eccentricity is there in the beam, or we can say that whatever the bending moment which is coming due to the application of load, it will tend the beam in a particular rotation. Beam is not in the equilibrium form, or there is a rotation is there in a beam. So we cannot say that actually whatever the beam or the moment which is considerable under the action of these forces are real satisfied or it is good. That means there is a faulty part is there in the consideration of the bending moment. And if the end is force or a pinned, means like the reaction forces, the component like the total whatever the components are there under these force, these application of these forces computed, sum must be like equal to 0. That means whatever the forces are coming in, as I told in the individual section, they must be well balanced under the application of these forces, and we can say that this pinned force or whatever this line force is, they are simply inducing this bending moment in the equating of a 0 part. If the end is built in, like whatever this and they are in within built in the portion is there, the bending computed by the summation must be equal to the one calculated initially for the reaction, because they are in built system. So when we are talking about a moment which is coming due to the eccentricity, they are always be calculated by the initial, whatever the initial reactions are there from the system concerned when you apply the load, and these conditions must always be satisfied. if we are saying that the bending moment is there or shear forces are there in a beam and they are under the application of these load conditions, we need to satisfy these conditions, and then only we can say that yeah, whatever the like conditions which we observed or whatever the sign convention which we took to analyze these like the shear force as well as the bending moment, they are really they are correct, and whatever the values are coming, they are perfectly in a right direction. Now you see whatever we discussed in these to calculate the shear force or bending moment, and also you see we discussed about that actually how we can which conditions have to be satisfied to check it out whether we are drawing the shear force diagram or bending moment diagram perfectly or not, or what will be the condition when like we have the shear force is 0 or we have the shear force is like the constant, then how this bending moment will vary. So all the discussion you see we would like to see in our real these numerical problems. So first of all we are taking some of the problems to check it out those phenomena. So in the following sections some illustrative problems have been discussed so as to illustrate the procedure for drawing shear force and bending moment diagram, and only we are just changing the domain to have a feeling that actually if the different forces are there and different domains are there, then how we can show the shear force as well as the this bending moment diagram for those things. So first of all, the cantilever, we have a cantilever, that means when we are saying that a cantilever, that means we have a beam, one end is rigidly fixed up and one end is free. So if you want to apply the load, only we have a free end where we can apply the load irrespective of load, bending moment, whatever like that you see. So you see if we are starting from a cantilever of a length carries the concentrated load W, that means you see only we have a point load at a free end. So it's pretty simple condition, this end this is fixed and the load is here at the extreme corner. So this load will tend to move this beam towards this direction, this rigid end tend to put a anti moment to balance this condition. So due to that you see we have a shear force, we have a bending moment. How to draw those things? Now the procedure is like that. First of all, at a section just take a section at distance x from free end, consider the forces to the left. So always you see go from that portion as we discussed, starting from the left hand portion, draw just that this distance x, that we have a dx section from this left hand section x, and then you see we know that since the forces are going towards this direction, that means you see what we have, the shear forces are like that. So F equals to minus W for all values of that segment x. Negative sign means the shear force to the left of the this cross section are in downward direction and therefore it is negative. As I told you if it is in the this way or if it is in the this way, then how the sign conventions are. So here you see on the left hand side what we have, the shear force is going towards the downward direction, and you see we have a negative F is there. And now taking the moment about this cross section which we have discussed, what we have now this value F is nothing but equals to minus W, and corresponding you see the bending moment will come. So bending moment is nothing but equals to minus W into x. Minus sign again because you see it is just going to move this particular bend in the sagging this hogging portion. So that means you see we have a negative part in that. So negative sign means the moment on the left hand side of the portion is in anti-clockwise direction, and therefore you see taken the negative accordance to the sign convention, or you can straightway go that if it is in the this hogging negative, sagging positive. So this is pretty common based on your IQ you can simply concern those sign conventions for this shear force plus minus, or this sagging hogging for bending moment plus minus sign. So that the bending moment now occurs at fixed end, that is m equals to minus W into L, because you see we are taking this L is the length. So obviously if we are going for an entire portion of the beam, the total length of L is there, because you see again this is a very common phenomena. If you want to analyze anything, as we discussed, we better start from a small cross section, take you see that okay at x axis you see we have this particular cross section, and then take the moment or the forces and then sum up all those forces for small sections. You can easily find it out the resultant shear force as well as the resultant bending moment. So now you see here, as I told you we have a this prismatic bar, that means you see the whatever the beam is there, that is uniform cross section, this point load is there, there is no load variation is there, only we are putting the load at the extreme corner of this end. we have the like the resist support. So we can simply like consider with the symmetric portion or symmetric part of this particular beam, we can say that m which is equals to minus wx, which also equals to minus wl. So this now you have the bending moment minus w into l, force which is minus w. So corresponding you see like with those values you can simply calculate like this total shear force as well as the bending moment, and you can draw, because now you have a clear feeling with the sign convention that actually how the variation of this like the shear force as well as the bending moment is. So from the equilibrium consideration, the like the fixing moment applied to the this fixed end, because you see we have a cantilever, so we have a fixed end which is equals to whatever the bending moment is there is in w into l, and the reaction which is like coming due to the shear forces is w. So come to that point, what we have like we have this cantilever. So the cantilever is this one, this is the rigid end, this is like the free end, and as I told you like we have a point load at the extreme corner of the free end. So this is extreme corner of the free end, the load w is there, which is the concentrated load. And now you see simply cut the portion at x distance from the left hand. So now we cut the section x to x1, okay, and we have, you see, the distance, this distance is x. So you see the total length, if I am saying that this x, so the total length is L. So you see for this particular portion, now we have seen that the shear force is minus W. So you see, since it is minus W and it is consistent, there is no force is there in the entire length of the beam except this portion. So this force must be, that means this force must be same, that means there is no contribution is there from any of the force component. So you see, if I am saying that this is minus W, so it has to be constant, and this is, you see, now starting from this origin where this is, you see, the W the F equals to minus W is there, from that end to that end this shear force will be occur on the beam, and it has a constant value minus W, and it is like summing up to the extreme end of the beam, up to the right end I should say. So this is my shear force diagram. So it's pretty rectangular form, nothing is there, and the rectangular form of this particular, this height is minus W because of the applied load, and it is consistent up to that portion. So we have this shear force diagram. So once we have the shear force diagram, then it's pretty easy for us to calculate the bending moment also. So one, like the shear force is nothing but it is F equals to minus W, irrespective whether starting from the cross section X or from the entire beam length. So now you see, like if we see on the same beam, and this like due to this applied load, if we have the bending moment, so it will vary like from the point of the origin of this load, and it will go up to the maximum where the fixed corner is. So because you see this m is nothing but equals to minus W into x. So if we keep the value of x equals to 0, probably like we have m equals to 0. So at this particular point where this origin is there, this bending moment is 0. Now if you keep this x is value is 1, 2, 3, if you keep on increasing those things, the bending moment will increase, and it will increase up to the extreme corner. So if we are keeping x equals to L, what we have m equals to WL, since they are in the hogging way, so it is in the negative way. So if we see on this particular diagram, we'll found that like this, it's a variation is in like this in a triangular way, starting from 0 to maximum of this corner, and the maximum value is minus W into L. So we'll find that this variation is pretty triangular way, or there is a linear variation is there as you keep on moving in the variation of the x. So you see here it's pretty simple. From this cantilever beam, if we have a W which is a single loading condition, if we have a single loading condition, then the contribution in the shear force as well as the bending moment is from only that load. So this is the applied load, the shearing load is coming from at the reaction part. So from these two parts, you see what we have a simple shear force diagram, rectangular part, and the triangular part bending moment diagram is, and the maximum value of the shear force is minus W, the maximum value of the bending moment is minus W into L, the minimum value of the bending moment is 0. So like that, you see, we can easily calculate all those things for a cantilever. Now the next case, if we are thinking about that, if we have a simply supported beam which is again like subjected to a point load, or we can say the concentrated load, and the location of this concentrated load is exactly at the midpoint of the beam. So now you see what we have, this beam is there supported at these two extreme corner, and the point load is there at the center position. Just see on this particular diagram, this is a simple like the uniform cross sectional beam. these two supports are there, like these, and when you apply the point load at the mid section, you see L by 2 and L by 2, that means you see we have a total cross section at the total length of beam is L. So, by like the symmetry, this symmetricity is there because the point load is at center point, the reactions are coming at the extreme corner, the length is L by 2, L by 2. So, from the symmetricity we have a similar reactions on the vertical top, the vertical topward this upward direction, and then like the magnitude of these reaction forces are also same, equal, and like the same direction, that is W by 2, W by 2. And now if we consider any cross section at any of, you see, from left hand like the portion, then the beam is under the action of these like forces. We have a symmetric reactions are there from both of the end, and then corresponding, you see, we can find out what will be the shear force and the bending moment is. So, you see, now considering the same part, you see we have like this L length same cross sectional beam, these two reactions which have the same magnitude, W by 2, W by 2, and acting towards the upward direction, okay. And you see this point load is there which is just acting downwards, and because of that, you see we have the shearing action in this portion as well as in this portion also. So, in that, you see, if you go for the left hand portion, like what we are doing here, we are first considering the XX portion. So, with this XX portion at the distance x, if you look at this point, then you will find that we have like the force which is going upward direction at the extreme corner, and this is positive, like this is going towards the downward direction. So, if we are checking this shear force in this direction, we have a positive shear force. Similarly, if you go on the other round like that, you see this section, okay, then you will find that this portion, the W is going downward direction and the reaction W by 2 is going on the upward direction. So, this one is there, that means we have a negative shear force. So, by considering this positive and the negative, since they are equal and opposite and like in the direction, that means they are cancelling each other, and we can say that the beam is under static equilibrium condition under the application of the force. So, by considering that concept, what we can do here, we can simply find out that what is the magnitude of the shear forces at the cross section, that would be always W by 2, which is constant up to x is less than L by 2, because you see after at x equals to L by 2 we have a additional W. So, you see it will add up in that particular part. So, now you see we just want to see that what will be the shear force diagram, then the shear force diagram is automatically like since it is starting from the this corner which is a positive corner, because as I told you this one is a shear force diagram portion which is positive. So, if you look at this point, then you will find that this is a beam at which the load conditions are, and this is the positive W by 2 up to this end, and then you see since it is positive W by 2, now minus W is coming. So, minus W will cancel out this positive W by 2, and additionally this minus W by 2 will also become, and this minus, because you see it is going downward from this end minus, and this is a positive one. So, you see this is like W and W by 2 will come. So, the resultant will come in a minus W by 2 constant up to starting from this point to this point. So, this is minus W by 2. So, we have two rectangles, one is positive of the left hand portion, one is negative at the right hand portion. So, you see we can easily find it out that actually what the shearing directions are, that how the shear forces resultants are coming, and how we can draw these shear forces if the point load is there at the extreme corner of a simply supported beam. Now, we would like to see that what the variations are there of a bending moment if this kind of shear force diagram is. So, this shear force, you see like we found that the variation of this shear force is exactly along with the load application on the beam. So, corresponding changes are there in the this bending moment also, that like because we told like we discussed that this either the shear force as well as the bending moment, they are the function of the x. So, we would like to see that how this bending moment variation is. So, for that we need to calculate the bending moment at the different sections, because you see what we have like the simply supported beam, do these two reactions, and the midpoint we have the W. So, for that again we cut like the XX section. So, first of all we would like to check that what is the variation is there in the bending moment at the XX cross section, and for that you see like starting from the reaction on the left hand corner W by 2. So, if we start from that point and if we just go towards that side up to the middle portion, then we found that this bending moment at XX cross section is nothing but equals to W by 2 into x, because you see like it is just lies in between 0 to L by 2, and for that like we can simply keep that if we start from x equals to 0 and if we are going up to x equals to L, then we have two different values. So, bending moment at x equals to 0, definitely it will be 0, because it is W by 2 into x, and it at L by 2 where you see the point load is there, we have bending moment at x equals to L by 2 which is W L by by 4. So, you see here what we have at starting point, that means the reactive point, since it is starting at the bending moment. So, we have a 0 value. If you move towards the middle direction where you see the point load is there, we have the maximum portion, that means that is the WL by 2, and then you see even if we go beyond XX point, that means up to YY point, then we have a different cross section, that means then we have different, like altogether the variation of the bending moment, and that is equals to W by 2 into X minus W into X minus L by 2, because that portion of this is X minus L by 2, that distance. So, now we would like to take the this interactive effect of both the point. So, one we have W by 2 into X and one we have W into X minus L by 2. So, you see what the interaction is there. So, minus sign will like gives you the clear interaction, and by keeping like manipulate by doing this manipulation, what we have Wx by 2 minus W into X plus WL by 2, or you see like these portion if you calculate, then you have minus W by 2 into X plus WL by 2. So, now what we have the variation with the X. So, now if we are changing the value of X with irrespective of 0 to irrespective L by 2 to L, then what we have, when we are keeping X equals to like L by 2, then we have the same value as WL by 4, and when we are keeping X equals to L, then we have the similar value minus WL by 2 plus WL by 2, or it is equals to 0. That means you see the conclusive part is that we have a simply supported beam. Two reactions are there at the two corners, simply like the this concentrated load is there at the middle point. So, the inductive effect as well as the shear force we saw, but here you see the inductive effect is that we have the 0 bending moment at the extreme two corner where the pin joints are there, and we have like the maximum bending moment, that the magnitude is WL by 4 at the middle portion of that where the point load acting. Okay, so you see here if we want to draw that part, then what we have this shear force, and now this is bending moment. These two reactive points 0 0, we have the maximum, you see like, so it is varying like that in this triangular one, or we can see like this one, this slight variation is there. So, upward and downward at these 2 points 0, this is maximum WL by 4, and this is you see the overall feeling of the bending moment. So, you see here the meaning is pretty simple. If we want to design a beam which is simply supported and the point load is there, we can easily find it out that the bending moment gives you a maximum value where there is a change in the shear force from positive to negative or negative to positive, whatever like that. So, you see here this we can have a clear feeling of this from this diagram. This is shear force from positive to negative. So, this one is the point where the variation F is there, which is equals to dm by dx, and it gives you like this is. So, it has a clear feeling, change of this will give you like the maximum bending value. So, this is you see like WL by 4 is the maximum value, and W positive is the maximum shear force, W negative is the minimum shear force, and this is the shear force diagram. So, it may be observed at the point of application of the like this load, there is an abrupt change is there in the shear force. You see straight change is there at this particular point, the bending moment is maximum, and that gives you like F equals to dm by dx. So, you see like whatever we discussed in the mathematical way, it was clearly like visualizing from these diagrams that if we are saying that W, which is nothing but equals to df by dx, or if we are saying d2m by dx square, can be easily find out that actually there is a variation straightway if the load application is there. So, abrupt changes are there in the shear force. Similarly, you see if we are saying that the F is equals to dm by dx, so wherever the abrupt change is there, we have a maximum bending moment. So, all these you see like the factors, they are very much correlating, and we can also have a clear feeling if we draw the shear force as well as the bending moment diagram for any kind of loading for either simply supported or this cantilever is. So, now the third case is that we have a same cantilever beam which the extreme end is rigid, one end is free. Instead of point load, now we have a uniformly distributed load which have intensity of loading is W, that means kilonewton per millimeter, that means W per unit length. So, and we would like to find it out that what will be the shear force as well as the bending moment diagram is. So, starting from that, you see it is the free corner, this is the fixed corner, and for you see this is the UDL which has the intensity W per unit length. Okay. So, from that now what our main concern is that what will be the shear force is there due to these application of load, because when the load application is there, the bending will tend to move towards the downward direction, but there is some shearing forces will occur at the junction, you see where the rigidness is there. Okay. So, from these like the junctional point, how the reaction forces are coming to balance those the forces which are coming due to this load intensity, and how we can make the this beam in an equilibrium manner. So, for that what we are considering, again the same similar procedure which we discussed in the previous section. Cut the beam in the x-axis section at the x distance, and for that you see like what we need to find it out, that what will be the intensity is there. So, that intensity is Wx, and the tendency of this Wx, the intensity of the load is towards the downward direction. So, now for that you see what we need to do, we need to find it out that how the shear force is varying. So, here you see the load is W per unit length. So, the total load is W if I am considering the x x segment. So, the total concentrated load is W into x. So, now W into x is there now, and this is acting on the downward direction, and the reactions at the junction, as I told you where the junction is there, the reactions are coming towards the upward direction. So, what we have the shear forces in this direction. So, if we have this kind of shearing forces, as I told you, the sign convention says you have to take the negative shear forces. So, for that, up to the x-axis cross section of the beam, the shear force at this particular x-axis where you see the dotted line was there is minus W into x, because W is nothing but what we have, this total this small w into x is there. So, W is this one, the intensity of load into x. So, this is your shear force which is acting at the x-axis section, and it minus sign as I told you because of this. So, this is there for equation 1, and if I am saying that if starting from x equals to 0 there is no shear force. So, if I am saying that if a shear force at x-axis section at the starting point where x is equals to 0, always you see shear force is 0 is there, and it has a maximum value where the reactions are coming on the top of a. So, shear force at x equals to L, it is equals to minus W into L. So, you see here it is a clear variation of the shear force from starting point to end point, because in the previous section you see we found that the shear force was very consistent. If starting point it has a maximum value, middle point it has it is the constant, or if any addition is there, there is a algebraic sum is there. But here you see there is an entire length of beam or entire span of the beam is loaded by this W. So, obviously we can easily calculate that because of the intensity of this load what the variation is there. So, the variation is at starting 0 to maximum minus W into L. So, you see here again if we want to plot that these the shear force at x-axis action is minus W into x, or we can say at 0 or minus WL, it will clearly give you the straight line relation and the bending moment at the x-axis section obtained by simply treating the load to the left. Always you see, because it is this bending is coming from the left, which is the free end, and it will tend to move towards the downward direction. Okay. So, you see from left arm, the left end of this x-axis section will concentrated load of the same value acting through the center of the gravity, because you see again I told you that we need to find out that what will be the CZ is there, where you see these force intensity will come, and therefore you see the bending moment can be easily calculated by at x-axis section is minus W into x, that is the load, into x by 2. So, this is the location where this because it is a symmetricity is there, so it will always act at the half of the portion. So, x by 2 is the location where Wx load is acting. So, due to that you see the bending is coming. So, bending moment at x-axis section is nothing but equals to minus W into x by 2. So, we have bending moment which is it is a pretty difficult the kind of behavior is coming, it is minus W x square by 2. So, now it is a square term is there. So, again you see you will have a different kind of relations, it is not the straight relations, now it is sort of the different relations as. So, the above equation is quadratic in terms of as I told you, and bending moment is plotted against x, this will produce a parabolic relation. So, as I told you it is not a straight relation, it is now a parabolic relation. So, x square equals to 4ay. So, starting from x equals to 0 to x equals to L, if you are keeping x equals to 0, obviously there is no bending moment at that particular point. If you go up to the L, we have you see minus WL square by 2, or we can say at x the other portion we have WL by 2 minus W into x. So, from that you see now we can easily plot that bending moment as well as the shear forces, and for that the same cantilever beam supported by these this rigid support, and this is free end, and you see the UDL is there, the uniformly distributed load which has the intensity W per unit length. Take the cross section x, and as I told you the shear force was minus the at the one corner it was 0, and at the extreme corner it was nothing but the minus W into L. So starting from 0 to minus W equals to minus W into L will be the will be the maximum shear force. We can simply plot it straight this line, which will give you the real feeling of the shear force when there is a UDL is there. So since you see here the reactions are coming, this is, you see, the total intensity is there. So obviously at this particular point, just look at this particular feature, at this point we have the maximum shear force. So we have to be carefully design these things, and this magnitude of the shear force is minus W into L. And then you see what we have now a parabolic relation is there in between, the variation x square with the load condition. So you see we can easily find it out that at the extreme corner, the extreme end corner, the free end, we have a 0 bending moment, and at the extreme end corner we have minus WL square by 2. So you see here, since it is a square term is there, WX square by 2 was there, and at x equals to L, WL square by 2. So at this corner we can easily plot those things in a parabolic way. So we have the bending moment diagram in a parabolic, or if bending moment is there in the shear force, it is the triangular way. So that was the condition when the cantilever was there, and now if you apply the similar uniformly distributed load on the simply supported beam, the similar kind of the behavior is there. If these two extreme corners, point load is this concentrated load which can be easily get it if you know the distance, this L and W is there. So the total W into L is there, which load is applied, and due to that the shear force as well as the bending moment will come. The reactions are there, which is due to the symmetricity, always will be equal to WL by 2 at this point, WL by 2 at this point, and both will be acting on the top of direction. So now if you want to compute the shear force, what is that? This WL by 2 is going upward direction. The load which is, you see, W into L will be going in the downward direction. L by 2 relation, L by 2, the point. So this and this. So this is now the shearing reactions. So what we have a positive sign on the left hand portion. So now you see here, the same which I discussed, the total load will be carried by W into L, and by symmetry of the sections we have W by 2, WL by 2, WL by 2. The reaction forces are, and then at XX cross section the shear force is WL by 2 because of the reactions, this particular reaction which is going upward direction, and you see the middle portion W into X is there. This is the total intensity of the load into X. So this will go in the downward direction. So we have a positive side here, WL by 2 minus WX, or we can say if you take the W common, then we have L by 2 minus X. So now by starting that, what we have is, it is a straight line relation, no square cubic term is there, and you see having a slope which is equal to the rate of loading or the intensity of this loading is, this is W. So at x equals to 0, what we have a WL by 2. So what is that now? At the beginning we have a shear force, it is not the 0, we have a shear force which is equals to the 0 part, and then you see if you go towards the on both of the side, then what we have minus WL by 2. So concerning with that, at x just WL by 2, WL by 2 and x by 2 is there, which is WX is the center position. What we can simply get, we can get, you see, the those bending moment also from those equations, because the whatever the load is coming, it is coming from the center, and the reactions are going on the upward direction. So we have bending moment at XX section, which is, you see, cutting at the middle portion, WL by 2, that is the total reaction into X, the reaction which is coming from the left hand side, this one into X, minus WX, which is the load for the XX cross section, the intensity W into X, the total load, into X by 2. So by taking sum of W and X by 2 is common, what we have L minus 2. So if we are starting from 0 and going to the L, so if I am starting at x equals to 0, this will gone. If I am doing at x equals to L, so obviously you see L by 2 and this will 0. So I mean to say that if a simply supported beam is there and the two reaction points are there, the bending moment will be 0 and bending moment will be maximum, where you see x equals to L by 2. So if you keep those things, then you have minus WL square by 8. So by summing up of all the relations, what we have pretty simple diagram. First of all, we have this shear force diagram, these two reaction forces WL by 2, WL by 2. So we have the positive WL by 2 in this way, because it is going in this direction, and then you see it is in this direction, this one. So it is a negative direction, and the variation is this. So plus WL by 2 to minus WL by 2, this shear force diagram will be like that. And bending moment, because you see it is a simple kind of these parabolic relations was coming. So we have like the WL square by 8, as I just told you, at the middle portion, but at these two extreme corner it was 0. So starting from this 0 going up to the maximum, where you see the change of shear force is. So it is pretty, again you see it is verifying the theory that F equals to dm by dx, wherever the change, the abrupt changes are there in the shear forces from positive to negative, the bending moment will be the maximum, and that the value is WL square by 8, and it is like that, you see. So you see, like in this chapter we discussed the four different cases. The first case was very simple, that if you have a simply supported beam, if you have a cantilever and only point load is there at the extreme end corner, like there is no load contribution is there, the shear force, and since it is going in the downward direction in this particular way, we have the negative. So a simple rectangular was there, and the same bending moment was pretty like the straight line, the triangular way is there, and both were in the negative. And then we discussed the second case, that if we have a simply supported beam and the point load is there at the center position, then you see like what kind of variations are there in the bending moment as well as the shear forces. Then like we found that since in both of the cases it is pretty like straight relations are there in the shear force as well as the bending moment, as you see the W is equals to dF by dx or d2m by dx square. But you see, as we go in the UDL part, that means the uniformly distributed load, then since shear force, it is a force part, so W into x is W is the intensity of the load, which is you see W per unit length. So whatever the total load is coming, that is W into x or W into L. So in the shear force, it has a clear contribution that is starting from like the 0 to it will go for the maximum at the at the extreme corner if the cantilever beam is there, or if we have like this last case where the simply supported beam was there, then it has a clear variation from WL by 2 positive to minus WL by 2 negative shear force. But if you are talking about the bending moment, then it has a parabolic relation. That means you see now there is not a straight line relation is there. If we have a UDL, we have a parabolic part irrespective of L square by 2, or like if the cantilever beam is there, or we have WL square by 8 if the simply supported beam is there. So we must know that if like the kind of variations are there, if whatever the kind of variations are there, it is due to the application of the load, that how the loads are applying on this particular beam and what the corresponding interactions are there in between the reaction as well as the application of load. So that we discussed. But you see, still whatever we discussed, we simply discussed that only one load is acting. That means you see, there is no interaction is there of the different kind of loading. We discussed starting from the point load only, that point loads are there on a cantilever or simply supported beam, and then in the next part we discussed that if UDL is there on a cantilever or simply supported beam. Now in the next lecture, you see, we are going to discuss about that if we have like the both two types of loadings are there together. That means you see, if we have a beam which is like the L length is there, in one portion of the beam is subjected by a point load, one portion of a beam is subjected by a UDL, then how the interaction is there. And that too, you see, this is only the loading. We also want to discuss that actually if there is a moment application is there, that means if any twisting moment or any couple is acting on a beam along with the variety of the forces, then how these like the forces and the moments are interacting to each other, and what will be the resultant shear force as well as the bending moment is. And those things you see, we just want to see on the shear force as well as the bending moment diagram with the kind of variation. So that is, you see, like in the next lecture we are going to discuss all these things. Thank you.
Thank you.